In this example, we're going to continue looking at the reduce and return method to find everything that we're looking for in the circuit. And we probably won't stop with just V1, V5, I2, and I6. We're going to find everything. So that's probably how I work a lot of my problems. So just be prepared. We're going to find all the currents and all the voltages throughout this circuit. So the first thing in the reduce and return method is we look for resistors we can combine. So in this case, I see a few things, right? It looks like R1, R2, and R3 are all connected here. You can use your colors and try to figure out what's going on, and they're also connected here. So whenever we see resistors that are connected in two places, we think, oh, those are in parallel. So I would call that RA, and to calculate RA would be 1 over 12K plus 1 over 12K plus 1 over 3K. So the total there would be 2K. If you're following along with the video, have your calculator out and try to calculate these yourself and make sure that you're able to use your calculator to get the right values. If you're not, please reach out and let me know. Okay, next I see R4 and R5 appear to be in parallel as well. Let's see if that's true. They're connected on the left, and it looks like they're connected on the right. So they are also in parallel. So I'm going to call that RB. And I'm going to calculate the total resistance there. And that would be about 3.6 kilo ohms there. So I'm going to stop there and just redraw my circuit. Notice that this these parallel resistors, if I put those terminals there and these resistors here, these terminals here, I can put RA on through across those terminals as I could put RB on at those terminals as well. So when I redraw my circuit, I'm going to try to keep it all on the same page here. I've got my 28 volt source. And RA is right here, which is 2 kilo ohms. I'm going to put RB right here, which is 3.6 kilo ohms. And then I didn't do anything with my 10.4 R6. Okay, so this I'm going to call my step 2. All right, now let's treat this like it's its own problem, okay? Like it's a totally new circuit. Sorry for the crooked there. You can draw yours neater on your paper. All right, so since I've got, now I want to reduce this a little bit further. So I look at RB and R6, and I notice there's one connection between them on this side, and there's nothing else connected between the two. So these are actually in series. So I'm going to call this RC. I'm going to call that RC right here, is RB plus R6, which would be 10.4 plus 3.6, or 14 kilo ohms. And that's all I'm going to do for this step. I'm just going to redraw the circuit. I'm going to remove RB and R6 from the circuit, and I'm going to replace them with the 14 kilo ohm resistor, because that's really the same thing, right? Now the question is where to draw that 14K. Well, it could go up where RB is, or it could go where R6 is. It really doesn't matter. I'm just going to draw it where R6 was. As long as it's on that branch, it really doesn't matter. So that's RC, which is 14 kilo ohms. And that would be our step 3. When we get to step 3, we just look at this as if it's its own circuit all over again. So we have another problem to look at here. And now I notice that RA is connected to RC up here, and it's connected to RC at the bottom, so they're in parallel. So my total resistance for my circuit, now that I'm down to just one resistance, is RA in parallel with RC. So I'm going to calculate the total resistance there, and I find that I've got 1.75 kilo ohms of total resistance. So I'm going to draw my circuit one more time to show that. And that is my fourth and final step in the reduce portion of this analysis. Now I do this because that enables us to find our I sub S, our source current. So I sub S is always going to be the supplied voltage divided by the total resistance of our circuit. So I've got 28 volts I've applied to what I now have learned is 1.75 kilo ohms of resistance, which means we're supplying the circuit with 16 milliamps. That 16 milliamps through our 1.75 kilo ohms means we've got 28 volts drop there. Again, Kirchhoff's voltage law, a rise of 28 volts has to equal the drop of 28 volts. So, and RT is in series with the 28 volt source, but also in parallel because they're the only two components in the circuit. So they have to be the same voltage drop. Now that I have found everything at this level, I'm going to transfer that knowledge up to the step right above it. So this is where we start the return portion of our circuit analysis. So I found out that I'm supplying 16 milliamps to my circuit. I also know that between step 4 and 3, or 3 and 4, I combined RA and RC in parallel. And what do we know about parallel resistors? The voltage is the same across each. So I'm going to have 28 volts here and 28 volts here. And that is going to help me find the current through each, because IA is defined as the voltage drop across RA divided by RA. So the voltage drop is 28 volts because RA is in parallel with the source over 2 kilo ohms of resistance, means that I've got 14 milliamps of current through RA. To find IB, we're going to do the same thing. The voltage drop across B divided by the resistance of B will give us that current. So 2 milliamps we'll see right here. Again, think of your Kirchhoff's current law at our node here. We have 16 milliamps of current coming in, 14 leaving through RA, and 2 leaving through RC. I should have named that C, huh? Sorry about that. Let's change this to C. IC equals VC over RC. Okay, I'm going to fix that. I just didn't look at what it was called. Okay, so that makes sense. Our voltage drops all look correct. So we found all the voltage drops and all the currents in step 3. So now we're ready to move up to step 2 and transfer everything we've learned up to step 2. Okay, so we've got 16 milliamps coming from the source. Through RA, we have 14 milliamps there and 28 volts of voltage there. So because RA didn't change between the steps, we can just transfer that straight up. Now what did change between step 2 and 3 is we combined RB and R6 in series. What do we know about series resistors? we know that the current is the same through each of those resistors, and we found the current must be 2 milliamps through each of those resistors. So since we split those resistors into series resistors, they divide our voltage. They're going to divide that 28 volts across the whole thing, proportional to the actual resistor values. So let's figure out what our voltage drops are. So the voltage drop across B is going to be the current through B times the resistance of B. So we found the current will be 2 milliamps there times 3.6 kiloohms, or that must be 7.2 volts drop there. The direction is going to be in the direction of the current. So the current comes in on the more positive side, and then we drop voltage across the resistance in the direction of the current because it takes energy to push that current through there. So there's VB. V6 is going to be the current through R6 times R6. Again, that's 2 milliamps because it's in series with RB, times the 10.4 kiloohms. So 20.8 volts we'll see drop across R6. Now that makes sense as well, because if we used our Kirchhoff's voltage law equation around this loop, we would see plus 28 through RA minus 7.2, which leaves 20.8. Minus 20.8 would get us back to RV equals 0 here at ground. Okay, so that makes sense. And now that we have found all of our currents and voltages at step 2, we're able to then return back to the original circuit. And we're going to transfer everything we've learned up to our original circuit. So we know that we've got 16 milliamps of current here. What else do we know here? We've got 14 milliamps through RA. Well, RA was this entire resistor network here. I'm going to get rid of some of the marks I've already made. So that 14 milliamps is going to be right here. And it's going into a current divider. So the 14 milliamps is going to split through each of those branches, and we'll figure out what that is in just a minute. But the voltage drop across RA was 28 volts. Since all of these resistors are in parallel, we're going to see that same 28 volts across each one. Okay, so you're going to have 28 volts across R1, R2, and R3. Okay, now we also have 2 milliamps going through RB and R6. Okay, so where is that? That's right here. And it's right here, okay, because it's going to split through these two parallel resistors, but then it'll come back together on this other end, okay? So let's transfer our voltage drops that we found here. R6 didn't change, so it's still going to have 2 milliamps through it and 20.8 volts across. And where is that 7.2 volts across RB? Well, this is RB, and these are parallel resistors. So parallel resistors have the same voltage drop. So that 7.2 volts you're going to see across R4 and across R5. So V5 is, of course, 7.2 volts. Now, what's there left to find? Well, there's left to find the current through each of our branches here and through each branch here. So we need to find about 5 more currents, and then we'll be finished. Okay, so let's start with I1. So I1 is defined as the voltage drop across R1 divided by R1. So for R1, we've got a 28 volt drop across 12 kiloohms of resistance. So that would be about 2 1/3 milliamps. Okay, so I'm going to draw that in. 2.33 milliamps. Okay, so I2 is going to be V2 over R2. Well, V2 is also 28 volts, and R2 happens to be 12 kiloohms as well. So we're going to have the same amount of current through there. It's not the same current, it's the same amount of current. So that's also going to be 2.33 milliamps of current there. And then the current through R3 is defined as V3 over R3, where we still have 28 volts drop across R3, and that's a 3K ohm resistor. So that's 9 1/3 milliamps of current through there. So 9.33 milliamps here. And again, do your little calculation coming in. We've got 14 milliamps coming into a current divider, 2 1/3 through R1, 2 1/3 through R2, so that's 4 2/3, and then plus the 9 1/3 going through R3, so that's 4, 5 plus 9 is 14, and then that'll be 14 again on the other side. And now we need I4, which is V4 over R4. So the voltage drop across R4 is the 7.2 volts, and that's a 9K ohm resistor. So there we'll have 0.8 milliamps, or 800 microamps if you like, 0.8 milliamps here. And then I5 is V5 over R5, or that same 7.2 volts, but this time across a 6K ohm resistor. So that would be 1.2 milliamps. So again, looking here at our node, we've got 2 milliamps coming in, 0.8 milliamps going through R4, and 1.2 through R5. So that adds up to 2, which makes sense. Comes back together again over here to be my 2 milliamps. Okay, so in this case, we have found everything that we were looking for. We found V1 is 28 volts, I sub S was 16 milliamps. Looks like we were looking for I2, which was 2 1/3 milliamps, V5, which was 7.2 volts, and I6 was 2 milliamps. We actually found all of the currents and all of the voltages throughout the circuit using the reduce and return method.